All right, I'm sorry about that. So as I was saying a moment ago, today we are going to be talking about filter circuits. Specifically, we are going to look at passive filters in circuits 2. And this topic, along with active filters, will be revisited in circuits 3 and the fall. So let's kick things off by what a filter circuit does. Filters are electronic circuits, or call it electrical circuits, which attenuate or suppress signals with unwanted frequencies. We deal with filter circuits every single day. Okay. Electrical filter circuits are what allows us to tune in to specific channels on our radio when we're driving to school or work. They are what allows our cell phones to send a call to a specific person or receive a call from a specific person. They are what helps to guide internet traffic to our devices. Examples of well, actually, I guess technically, our eyes are actually electrical filter circuits, in as much as light is an electromagnetic wave, and our eyes filter out all light that isn't in the visible light frequency range, allowing us to see the different colors. In fact, some people's eyes are better or worse filters than ours. There have been documented cases of some very small subset of people actually being able to see infrared radiation as well as UV radiation. Okay, so filters are all around us, and we are just going to get our toes very, very lightly dipped into the pool. The first thing that I want to talk about are the general classifications of filters, and we're going to look at these through the lens of an ideal filter, or what the ideal response might look like. All right, so we're going to do this by looking at plots. And so our first plot is going to be of this form. Our x-axis will be angular frequency, and our y-axis will be h as a function of omega. And I'm going to express this as the magnitude of a complex number because that's what we'll actually be dealing with. And this is simply the ratio of the output phasor voltage divided by the input phasor voltage, both as functions of frequency. So the first filter that we're going to look at has a response like this. Okay. So signals get passed completely up to a certain point, after which attenuation occurs. This certain point here, we are going to call omega C, which stands for our corner frequency. And it tells us when our transition occurs. Everything to the left of omega C in this particular filter is known as the pass band, because all signals with frequencies less than omega C get passed or scaled by a factor of 1. And everything to the right of omega C is what's called the stop band. All signals having a frequency greater than omega C become completely attenuated. So this particular circuit is what's known as a low pass filter. This is an example of an ideal low pass filter because of what we call the brick wall response, where what the brick wall response means is effectively there is not a gradual transition between the pass band and the stop band. At a very specific frequency, all of a sudden signals start to be attenuated. In a practical low pass filter, we'll see that there is a gradual transition from the pass band to the stop band. We will have a corner frequency, but this corner frequency will have a very specific meaning that we'll talk about in a little bit. All right, so our second type of filter, where again, this is the magnitude of h of omega. This axis is omega, is the exact opposite of a low pass filter, in as much as signals are completely attenuated up until we hit our corner frequency, at which point signals begin to be passed. The height of this guy is 1. Now we have a stop band on the left and a pass band on the right. And this is what we call a high pass filter. Before we introduce the other two types of filters, I want to mention something here. This generic low pass filter and our generic high pass filter can be realized with what I'm going to call first order circuits, which are circuits that contain a single energy storage element. So an RL circuit or an RC circuit can be used as both a low pass filter and a high pass filter, and we'll see examples of how that's done. Now, we can realize them with first order circuits. However, they can also be realized with any order higher than 1. So we could have 2 energy storage elements, 3 energy storage elements, 30 energy storage elements, and still get high pass and low pass filter responses, okay? So these are kind of like our fundamental building blocks of filters because they can be implemented with the least amount of components. The next two that we're going to talk about require at least a second order circuit or a 2 energy storage element circuit to realize. So the next guy that we're going to look at is this one. And this is a combination of a low pass filter and a high pass filter. So in this particular circuit, we attenuate everything until a certain point. I'm going to call this frequency omega low, at which point we begin to pass signals until we reach a second frequency, which I'm going to call omega high, and then we attenuate everything again. There is also a frequency here in the middle. And I'm going to call it omega naught. Some textbooks, you may also see this as omega C, but it would be a center frequency. I find that confusing. Really, omega low and omega high are our corner frequencies in this circuit, and omega naught is the center frequency or resonant frequency of the circuit. Okay. So we have a stop band over here on the left. Pass band here in the center, and then another stop band here on the right. This circuit is what's known as a band pass filter. And it has a bandwidth equal to 1/2 pi multiplied by omega high minus omega low. Our last of our 4 classifications of filters is also a combination of a low pass filter and a high pass filter, and it is the opposite of the band pass filter. So in this filter, we are going to have a pass band, or we're going to pass all signals until we reach omega low, at which point we begin attenuating. And then when we hit omega high, we're going to start passing signals again. This circuit also has a center frequency omega naught. On the left here, we have our pass band. In the middle, we have a stop band. And on the right, excuse me, we have our second pass band. And so this is known as a band stop or notch filter, which also has a bandwidth of 1/2 pi times omega high minus omega low, where in this case the bandwidth corresponds to the frequency range over which all signals are attenuated. Okay. All right. So these are our 4 different classifications of filters: a low pass filter, a high pass filter, a band pass filter, and a band stop filter. This is just one way of describing the different types of filters. Okay. You may have heard of things like Chebyshev filters, Butterworth filters, things like that. Those are specific circuit topologies used to realize these 4 classical filter types. Okay. So we are looking at filters from a perspective of what they do right now versus how they're made, which will be how we look at them later on. All right, so let's look now at a practical filter circuit. So I draw my circuits, and you'll see them like this, especially for passive circuits, where my input signal is on the left-hand side and my output signal is on the right-hand side. So on the left-hand side here, I have my pair of terminals at which my phasor voltage Vn is applied. And then what I'm going to put here is some resistor. Then I'm going to have a capacitor. And since we are in the frequency domain, I'm going to draw my capacitor and realize it with its impedance, which is 1 over j omega c. And then out here, it's going to be the output side of my filter circuit. V out of omega. The response of a filter circuit is H of omega, which is what's called the transfer function of the filter circuit. This is a ratio that is simply made of V out of omega divided by V in of omega. So we can really think of this transfer function as kind of like a frequency dependent gain for our system, right? Or frequency dependent voltage gain very specifically, because we're looking at output voltage over input voltage, okay? So for this particular circuit, we can see that our output voltage V out as a function of omega is simply the in of omega multiplied by the ratio of 1 over j omega c divided by r plus 1 over j omega c using voltage division, okay? And all of these filter circuits that we're going to look like are really just simple voltage dividers, where we have a frequency taking the voltage drop over a impedance that has a dependence on frequency. So from here, H of omega is then just the ratio. So let's write this out more formally. V out over omega over V in over omega. And this is just that ratio of 1 over j omega c divided by r plus 1 over j omega c. So we could stop here, but typically speaking, I'm going to get rid of the fractions inside of this ratio. So I'm going to multiply this by a factor of j omega c over j omega c, which gives me 1 over 1 plus j omega rc. I'm going to put a box around this, because if I were to ask you to determine the transfer function of a circuit, this is the type of form that I would expect. Simple fraction without any fractions in the numerator or denominator of the ratio, okay? Now, h of omega, our transfer function, is a complex number. And so it can be broken down into two parts. The magnitude response, or more commonly called the frequency response, which tells us effectively how the attenuation occurs as a function of frequency. And then we have a phase response, which tells us how the angle of our response changes as a function of frequency. Now, recall from our Circuits 1 lecture on complex numbers that the magnitude of a complex number A is, actually, hold on. So if I have a complex number A is equal to A plus JB, this is my rectangular form for a complex number, then the magnitude of A is given by the square root of A squared plus B squared. And the phase angle of complex number A is given by the arc tangent of the imaginary part B over the real part A. Well, we are going to use these three relationships in order to determine our magnitude response and our phase response. In order to do that, we need to take the transfer function that I have outlined here in blue and express it in terms of a rectangular complex number. Okay. So come down here. Here we have h of omega is equal to 1 over 1 plus j omega RC. And what I'm going to do to split this up into real and imaginary parts is I'm going to multiply this ratio by the complex conjugate of the denominator over the complex conjugate of the denominator. So that's going to be 1 minus j omega RC over 1 minus j omega RC. And so when I multiply my numerators together, I obviously just get 1 minus j omega RC. When I multiply my denominators together, I get 1 plus omega RC quantity squared. And now I'm going to split this up so that I will have 1 over 1 plus omega RC squared minus j times omega RC over 1 plus omega RC squared. And now I have this split up into a real part A and an imaginary part B. So now let's tackle our magnitude response. The magnitude h of omega is simply going to be the real part squared plus the imaginary part squared and then we take the square root of this whole thing. All right, so I'm going to have the same denominator, so we'll get to that bit in a moment. But looking at the numerator, effectively, once I square them, I'm just going to be able to add everything up. So this is going to look like 1 plus omega RC squared divided by 1 plus omega RC squared quantity squared. Are we okay with the algebra there? All right, since nobody's saying no or typing anything into the chat, I'm going to assume we're all okay. Obviously, this bit right here cancels out this power. And so what we're left with is 1 over the square root of 1 plus omega RC squared. So this is what our magnitude response looks like. Now what we're going to do is use this information to figure out what kind of filter we have, okay? So if we evaluate this expression at omega is equal to 0, what would we get? Well, when omega is equal to 0, in our denominator, we're going to have the square root of 1 plus 0 squared, which is the square root of 1, or 1. So we have a numerator of 1 and a denominator of 1. So h of 0 is 1. Now we're going to look at things when our frequency is infinity. Okay. So when our frequency is infinity, we're going to have the square root of 1 plus infinity squared, which looks like the square root of infinity squared, or infinity. Well, 1 over infinity is effectively 0. So from this, we can see that our circuit passes low frequency terms and attenuates high frequency terms, which means this is a low pass filter. Now, I'm going to plot our frequency response here. It's going to look something like this. And this is a value of 1. And we are going to now define our corner frequency. So omega C will occur when our magnitude has a value of 1 over the square root of 2. This is what's called our half power frequency, okay? Also known as our minus 3 dB frequency, okay? So on a logarithmic scale, 1 would correspond to 0 decibels. And whenever the value is 1 over the square root of 2, this would correspond to -3 decibels. Okay. So our half power frequency is our corner frequency for these practical filters. Because at any point before we hit omega C, at least half of our signal power is reaching our load. Half of our input signal power is reaching our load that's connected to the filter. And beyond omega C, less than half of our input signal power is reaching the load. So this is an arbitrary place where we defined our corner or cutoff frequency for our filter. All right, so now let's figure out when this occurs, okay? So what value of omega will make our expression look like 1 over the square root of 2, okay? So effectively, what I'm saying here is we have 1 over the square root of 1 plus omega RC squared. And this is equal to 1 over the square root of 2 when omega is equal to omega C is equal to what? Well, it's pretty obvious here that the quantity omega RC needs to equal 1, right? Because then that would give us a 1 over the square root of 1 plus 1. So omega RC needs to equal 1 implies that omega needs to be 1 over RC. So our corner frequency for our low pass filter is established by the resistor and the capacitor value such that our corner frequency is equal to 1 over RC, okay? So this is how we choose what signals to pass and which signals to attenuate. All right, now let's look at our phase response. Oh, sorry. Theta as a function of omega is the inverse tangent of B over A. So this is going to look like the inverse tangent of, let's go back a page and look here. Omega RC, excuse me, negative omega RC over 1 plus omega RC squared divided by 1 over 1 plus omega RC squared. This and this cancel out. And what we're left with is the inverse tangent of negative omega RC. So this is what our phase angle response would look like. All right, give me just a moment here, and I'm going to pull up LT Spice. All right, so we are going to talk about how we could simulate a simple filter circuit like the one that we've just drawn. Okay, so the first thing I'm going to do is I'm going to put a voltage source in. And this is our input voltage. I'm going to leave it blank for now, and then we'll talk about what parameters we would need to put in. Up here, I'll have my resistor value. Somebody type a number into chat for the resistor. $10 kiloohms. Thank you, Matthew. In this branch, I'm going to have my capacitor. Somebody give me a capacitor value. $250 micro, alrighty. I am going to put this node as my ground. I am going to label this node over here as V out. And this is my input voltage. I'm going to go to the advanced tab. And what I'm going to do is I'm going to go over here to where it says small signal AC analysis. And I'm going to type in an AC amplitude of 1. So what that means is that our input signal will always have a value of 1 volt, regardless of what the frequency is. Okay. The reason I'm doing this is because our transfer function is V out over V in. If V in is always 1, if we plot V out, then we effectively have our frequency response that we're looking for. Okay. And now I'm going to edit my simulation command, and I'm going to go to AC analysis. So we are going to do a decade sweep. Let's do 1,000 points per decade. Let's have a start frequency of 1 millihertz and a stop frequency of 1 megahertz, and then we'll adjust from here as needed. And I'm going to run my simulation. And I'm going to plot V out, which again is nothing more than our transfer function. Okay. So the graph that we get in LT Spice is composed of 2 different parts. Okay. The solid line is our magnitude response, and the dashed line is our phase response. Okay. So what I'm going to do now, and I've got a, sorry, I'm trying to move the Zoom stuff out of the way so that I can see better, is I'm going to click here. And it brings up this little menu, which lets us see what our magnitude is as a function of frequency, as well as our phase angle and a couple other parameters that are beyond the scope of this class. And what I'm doing is I'm just moving this thing to the left until my magnitude reaches -3 dB, or as close to -3 dB as I can get it. There we go. Okay, so according to our simulation, our circuit has a corner frequency of 63.833 millihertz. So what I'm going to do is I'm going to type in 1 over RC. So that's 10 kilo ohms, so 10 times 10 to the 3 multiplied by 250 times 10 to the minus 6. And what I get is 0.4. Okay, exactly 2/5. Okay, well, exactly 2/5 doesn't match 0.063833. The reason why it doesn't match is because the frequency that's given here is a linear frequency, but we have been dealing with angular frequencies. So if I take this factor of 2/5 and divide it by 2 pi, I get 0.06366, which is 63.66 millihertz. So our mathematical analysis matches that of the simulation. We just have to be careful because we typically in our classwork work in terms of angular frequency, and LT Spice gives us results in terms of linear frequency. All right, so any questions regarding this simulation? All righty, thank you. So let's go back to this stuff. Give me a moment to readjust my setup for writing on the screen again. All right, so now we're going to look at a second circuit. This is the exact same thing that we just looked at. So here is our input voltage. But now we're going to switch the position of the capacitor and the resistor. So this particular circuit is going to have a transfer function of R over R plus 1 over J omega C, or J omega RC divided by 1 plus J omega RC, which I got by multiplying the numerator and denominator by a factor of J omega C. So this is my starting point for my transfer function. From here, I'm going to break this transfer function into its real and imaginary components. So I'm going to have J omega RC over 1 plus J omega RC times 1 minus J omega RC over 1 minus J omega RC. And so this is going to look like, so when I have J omega RC times negative J omega RC, that's going to look like negative J squared, which is positive 1. So I'm going to have omega RC squared plus j omega RC divided by 1 plus omega RC squared. And breaking this up, that looks like omega RC squared over 1 plus omega RC squared plus j omega RC over 1 plus omega RC squared. So I have my real and imaginary components. My magnitude response then becomes the square root of the real part squared. So 1 plus omega RC squared, square this whole thing, plus the imaginary part squared. Taking the square root of this whole thing. So this is going to give me omega RC to the 4th power plus omega RC squared over 1 plus omega RC squared, quantity squared. On the same line here, I'm going to factor out a common factor of omega RC squared. So we're going to have omega RC squared times 1 plus omega RC squared over 1 plus omega RC squared squared. This bit cancels out 1 power, and we are left with omega RC over the square root of 1 plus omega RC squared. This is what our magnitude response looks like. Now, to determine what type of filter we have, we evaluate at 0. So at omega is equal to 0, we're going to have 0 over 1, which is 0. At infinity, we're going to have infinity over infinity, which looks like 1. So we attenuate low frequency terms and pass high frequency terms. So this is a high pass filter. Simply swapping the position of the elements changes the filter type. Okay. If we were to plot this, our graph would look something like this. Where this corresponds to 1. Here is our corner frequency, which again occurs at 1 over the square root of 2. So this is our half power or minus 3 dB frequency. So again, what we want is effectively omega RC divided by the square root of 1 plus omega RC squared to be equal to 1 over the square root of 2. And this happens when omega C is also equal to 1 over RC. So if we sub in 1 over RC, we get 1 over the square root of 1 plus 1, or 1 over the square root of 2. All right, our phase response is going to be the arctangent of the imaginary part. So I'm just going to scroll up here. Omega RC over one plus omega RC quantity squared divided by omega RC squared over 1 plus omega RC squared. So these guys cancel each other out. This cancels out 1 power of that, and we're left with the arctangent of 1 over omega RC as our phase response. All right, so we don't really have enough time to go through the inductor ones. But instead of leaving it fully as an exercise for you guys, I want to look at these last 2 examples from a slightly different perspective, kind of a qualitative perspective where we're really not going to worry about determining the exact magnitude response and phase response, but more focus on, in general, how we might figure out how these circuits behave, and then we'll apply that to our inductor circuits. So I'm going to go back a little bit here. And we're going to look at this circuit. And just by inspection, figure out what type of filter circuit it is, okay? So for this circuit, we are taking the voltage drop over the capacitor, right? Well, the capacitor is a frequency-dependent impedance. At very low frequencies, the capacitor looks like an open circuit because we're going to have 1 over J times 0, right? And 1 over 0 is infinity. So we have an open circuit, and effectively all of our signal at the input gets passed to the output. At very high frequencies, our impedance of 1 over J omega C starts to look more and more like a short circuit. So at high frequencies, we're taking the voltage drop over a short circuit, which must be 0. So we know that this circuit then passes low frequency signals and attenuates high frequency signals. So this is a low pass filter. If we look at this guy, at very low frequencies, again, our capacitor looks like an open circuit, which effectively disconnect our input voltage from our output voltage, okay? So if we aren't able to effectively drive any current through our resistor R, then our output voltage has to be 0. So at very low frequencies, this attenuates our input signal. At very high frequencies, our capacitor, again, looks like a short circuit. And so V in and V out are effectively in parallel. So for very high frequencies, all of our input signal gets passed to the output. And so we have a high pass filter. Okay, that's our kind of qualitative approach. Now let's do that for our inductor circuits. So if I have this circuit, what can we observe? Well, our output voltage is nothing more than the voltage drop over the inductor, right? So at low frequencies, ZL approaches 0 ohms or a short circuit. Thus, the out must also approach 0 volts. At high frequencies, the impedance of the inductor approaches infinity ohms or an open circuit, and thus the out will go towards the in. From this, we have a high pass filter. And I'll leave it up to you guys to figure out what the exact magnitude and phase response would be. If we switch the position of our components, at low frequencies, in this case, ZL goes to 0 ohms. And thus, V out will go towards whatever value Vn has. At high frequencies, ZL goes towards an open circuit. And thus, the out, sorry, my screen keeps scrolling on me. Oh my goodness. Goes towards 0 volts, since our input voltage is effectively being disconnected from the resistor. So we have a low pass filter. And again, I leave it up to you guys to actually do the math involved. I will give you a hint if you choose to do it. Your corner frequency in each of these cases should wind up being R over L. If you get that, you've been doing it correctly. All right, so that's enough out of me for today. What we are going to do on Wednesday is we are going to take a look at second order filter circuits. We're going to pay a good bit of attention to a band pass filter. So we're going to start our discussion there. We're going to look at a band stop filter as well. And then very, very briefly go over a second order high pass filter and a second order low pass filter. So effectively what we're going to do is we're going to have a series RLC circuit, and we're going to talk about the 4 different ways that you can develop a filter out of that. All right, unless anybody has any questions, I will see you all on Wednesday.